Okay, so we saw UCB. That's a pretty useful exploration strategy with some nice theoretical guarantees which we didn't discuss, but you're more than welcome to read more about that. A second approach that I would like to discuss is what's called the policy-based algorithms. So up to now we've seen, let's say, value-based approaches. I mean, we only saw Q-learning, but later on we'll see how to generalize such approach to states, value learning and stuff like that. So it's a more of a general class of algorithms. And now I would like to discuss a different general class of algorithm. Again, we're going to discuss it in the context of multi-armed bandit, but later on we're going to generalize these approaches and these ideas to general MDPs and general reinforcement learning. So the main motivation here is that we don't really care about Q values. That is, when we define a Q value and we try to learn that Q value, we're only doing it in order to allow us to later infer the optimal policy, right? And so a different approach might be, let's try to directly learn a policy without learning something in the middle. How can we do that? So we're going to see several approaches. As I said earlier, this is a general class of solvers, the policy-based algorithms. But for now, let's look at the simplified solution, specifically in the multi-armed bandit case. So a simple idea would be as follows. Let's assign a preference to each action, to each one of the actions, and then tune it. And we'll tune that preference. Okay. So let's define a new function. Okay, we'll call it h, capital H, at a given time step t of an action A. So later on when we discuss general MDPs, it will also be a function of the state and action. But for now, we're discussing stateless MDPs, right? So we only have actions and the state always remains the same. So let's say that each action has some numerical score associated with it. We update that score. And once we have a preference, some score to each one of the actions, now, again, we need to decide which action to select. Which action should we select?
The argmax action.
I mean, yeah, if age of t represents preferences, then yeah, we can go with argmax. If it represents, I don't know, a negative score, we can do argmin, but usually we look at this as a preference, right? So we want to go with argmax. Argmax will probably be a good starting point at least, right? So we can say, well, the action that we choose is the one with the highest preference, the one with the highest score. What's the problem with that? Argmax?
That there won't be any exploration because you always choose the greedy action.
Argmax tends to converge on that. Specifically, if you're only going to update based on observations, you're only going to observe action A and you're going to stick with it, right? So a hard argmax, that's usually problematic with respect to exploration. Right, this is a deterministic action selection. What can we do? So we saw several solutions to this, right?
Yes, so one was epsilon greedy, but the problem with that is we don't give preference to more likely actions and we give equal preference to even bad actions. Yeah.
Actually, softmax, sorry, not softmax, the epsilon greedy has another issue that we didn't discuss so far, but it will become a big problem here in a policy-based algorithm, which is epsilon greedy is not differentiable. You cannot take a derivative with respect to the action you chose. And I know that it sounds a bit, what are you talking about? Of course, we'll explain it, don't worry about that. But a different solution, one that also provides us with differentiability, would be indeed the softmax function that results in it's also known as Boltzmann distribution. So you apply the softmax function and you get a Boltzmann distribution. We'll define it in a second and we'll see why this is very helpful in policy-based approaches.
Professor?
Yeah.
In the previous slide, it seems like we've replaced the Q term in the argmax equation with a new H term. How do they truly differ?
So you're right. The H function, as we defined it here, is very similar to the Q function that we previously defined. Right? So previously we said we have a Q function for each. It provides a numerical value for each action, and higher Q values are better. And now, right, this capital H function seems very similar, right? But the H function is actually more general in some sense. So what we call it H at the moment. Later on we might have different notation, but for now it's an H. It's a bit more general in the sense that the Q value, as we defined it previously, it has a very specific definition. The Q value equals or should converge on the sum of discounted reward from being at a specific state S, taking a specific action A, and then following either a specific policy or the optimal policy. There is a very specific Q value that we're trying to converge on. Here, the H function is much more general. I'm not telling you what the value should be. I'm just saying, hey, I would like to assign some values such that the best action to choose will get the highest score.
Okay.
So they're kind of the same, but this is a more flexible function. It might be easier for us to fit it, right? If we have a function approximator that's not very expressive, well, we might be able to easily fit a general H function much easier. It will be in many cases much easier than a very specific Q function. Okay?
Thank you.
Sure. Okay, so let's define the softmax function, which results in a Boltzmann distribution. So the input for a softmax function would be a vector of scores, and the output should be a vector of probabilities that form a valid distribution. So the output should be a distribution. However, if the output is per action, then the output is a specific probability. However, the probabilities of all of the actions should sum to 1, right? It should be a valid distribution. So how is this function defined? So for each action, what we do is we output e to the power of that specific action, the one in question that we provided as an argument, over a summation of exponents of all, a summation of exponents over all actions, actually, including the action in question, okay? All actions in our action space. So this, we won't prove it, but you're more than welcome to look up Boltzmann distribution online. This is guaranteed to result in a valid distribution. Even if your scores are negative or come from various ranges, it will always squash them to be a valid distribution. Okay, so let's look at an example. What does that mean? So for instance, if we would like to pass, if we have an action space with 3 actions, A1, A2, and A3, and each one of them is affiliated with a specific preference, as we can see here. Okay, so action 1 has a value of 6, action 2 has a value of 9, and action 3 has a value of 2. By the way, as I said before, these can also be negative values, and you'll still get a valid distribution. And now we would like to apply the softmax function over these actions. If you plug in the values, you'd see that, for instance, for action 1, it will result in a probability of 0.047, for the value of 9 a higher one, and for a value of 2 the lowest one. You can see that the probabilities are correlated with the score values, right? This is exactly what we wanted. That is that the action with the highest score will actually result in the highest probability. And you can see that this makes sense. And of course, these are highly skewed, right? So the 9 has a much higher probability than the others. We can also include a parameter here, a hyperparameter here, that shifts the entropy of this distribution, how uniform it is, or towards uniformity. Don't worry too much if you're not familiar with the term entropy. We will discuss and define it later on. But for now, just know that there are ways to also play with this distribution. Because one might say, listen, yeah, you have a distribution, but the probability of actually choosing action 3 is so low that it's practically, well, it will happen very rarely, and we'd like to inject more exploration into our process, we can do that. Okay, of course. We can add a hyperparameter that tunes this issue.
Professor?
Yeah.
Here it seems like this would only work for a discrete action space. Would this also apply for an action space with continuous actions?
So we could. The answer is yes, but it's a bit more complicated. So for now, let's and we won't use it. Okay, so for now, or for the purpose of this course, let's just assume that will apply softmax over discrete action spaces. However, there are solutions to do it over continuous action spaces. But let's put that aside for now. You can read about that, of course, if you just Google. Okay, so right, we discussed that. That is, we have a valid distribution over the action selection. So I would say exploration checked, right? Oh, so here we are. So for a softmax function, we have exploration check. It's checked, right? It's baked into the process. We have exploration. And softmax provides another important attribute, which is a differentiable policy. And now we would like to discuss that because this is very important for policy-based algorithm. So what does that mean? So say that we learned that an action A1 results in good relative performance. Okay, so assume the multi-arm bandit problem and we play action number 1 and we actually observe a good outcome. So what should we do if we use reinforcement learning principles?
We should give it a good reward.
No, we observe that if we observe a good reward for a specific action,
we should do it more.
Right.
Yes.
We should reinforce
that action.
That behavior.
Yes.
Right. Yeah, that's the whole point in our course. Okay, so how can we reinforce the behavior? Right? In a value-based method, you say, yeah, well, not a problem. I'll just increase the value of that action. But now we have a policy-based approach, and the same question applies. So if we were to select a hard max operation here over the actions, and I would ask you a question, okay, how can we change the value of action number 1 such that the probability of action number 1 is increased? So you'll say, well, no problem, I know calculus, right? So I'll say it's the partial derivative of the probability of seeing action 1 over the score that we assign to action 1. This is how to change action 1. It's a partial probability because you can also change the score for action 2 and action 3 and still impact the probability of selecting action 1. But just to answer the question here, which is how to just change the score for action 1. So now you might say, well, that's kind of impossible, right? We cannot compute a derivative over a hard max function. It's a step function. There's no derivatives, right? I can't tell you from this hard max function, I can't tell you how to change the score such that the probability increases. I mean, I can tell you, you can say it intuitively, right? Sure, increase the score. If you increase it to a specific level, then it will become the dominating strategy. But I'm looking for a more of a gradient-based solution, right? And so in this case, the differentiability is very important. Now, what would happen if we, instead of a hard max function, we use a soft max function? I'm feeling like a weatherman here. So sorry, yeah, I have a green screen behind me. I can just see myself, see the actual slide in the screen in front of me. Okay, so let's say that we now use a softmax exploration function. So now I can ask again the same question. That is, how do I change the score that I assign to action number 1 such that the probability of selection action number 1 is increased? So now I do have a differentiable function. Softmax is a differentiable function, and I can actually compute this gradient, this magnitude of change and the direction in the change to age of A1 such that PR of A1 is increased. Okay, it's well defined here.